Welcome to everyone. So today's speaker is Osman Ismail, and he's a CTO and co-founder of Bedrock Systems. And the topic about today's talk is the TCB, so the concept of TCB and problems in applying in practice this idea on real-world software.
Thanks for the introduction. So good afternoon, everyone. So welcome to my talk, the TCB from assumption to insurance. But first, a little bit about myself. So my name is Osman Ismail. I worked at Sun Microsystem and Sun Microsystem Labs. I worked on network protocol stack a long time ago. I worked on PPP when modem was a big thing, so you can see how old I am. So I also work on Java virtual machine for embedded when Sun was trying to target the embedded system. And I also work on microkernel. So I then, in 2000, I left Sun. I joined a startup in the Silicon Valley called TerraSpring, and we were doing data center virtualization using all the management interface of the equipment to recreate a compute and network and storage element. And then this company would get bought by Sun. And after 2 years, so I went back to Sun. After 2 years, I left Sun again and joined FireEye. I was a founding member of FireEye. And FireEye is known for the first product for malware detection using virtualization. It was a very successful product. We had a very good customer was very happy about that project. And today I'm at Bedrock Systems. So I'm a co-founder and CTO of Bedrock Systems. And Bedrock, the Bedrock idea was started a few months after I left FireEye with discussion I was having with previous colleagues like Ashar Aziz and Udo Schneiderberg on how we can reuse some of the technology we work on the past to recreate a secure and strong foundation for the software stack of the new IoT world. That was the idea when we started 2 years ago. So about the talk, so the talk is about TCB, so I will define what a TCB is, and then I will also describe a real case application, expose what are the problems, I will propose an alternative, then go to conclusion, and after that I will take questions. So what is a TCB? So the first definition of a TCB appears in November 1979 in the specification of trusted computer bits. And it was refined and well known, in fact, for the definition that appears in the Orange Book in December 1985. And the text says, the trusted computing base is the totality of protection mechanism within a computer system, including hardware, firmware, and software, the combination of which is responsible for enforcing security policy. And security policy is, as usual, around confidentiality, integrity, and availability. But if you up-level a little bit, what you should think about is, what do you trust to run your application? What do you trust to run your system? So this is what the TCB is about. I want to introduce two important properties that I will use during my talk to expose different problems and different solutions that we can have around those. The first one is the TCB perimeters, which define the set of API which control the access to the TCB, and that will be access from the outside to the TCB and access from the TCB to the outside. And the other important notion is the notion of security or protection domain, which is a collection of objects that a process has access to with this level of privilege. Right? So it's really about access control mechanism to provide protection against unauthorized access to some data. So a real case application, and let's see what the problems are. So for a real case application, I took a web server because we all are facing or using a web server every day. So to set up a web server, you need the hardware and some storage for storing your data. There's the firmware, which go with the hardware. Then you need an operating system kernel. And on top of that, you will need a web server, a cache, usually they go together, and some runtime plugin like PHP, Python, JavaScript, or Java, and a database to manage your data very efficiently. And the question to ask is, what is the totality of protection mechanism responsible to enforce integrity, availability, confidentiality of my data, right? Furthermore, so in that picture, in that architecture, we have two clear separations. So there's one between the hardware and firmware to the operating system. It's somewhere in the firmware, a little bit blurry where exactly, but it's somewhere defined in the firmware, enforced by the firmware. And then there's the kernel and user space privilege enforced by the operating system, which define protection between application running in user space and those applications running in kernel space, kernel being a higher privilege component. And you also have this separation providing by the kernel, enforcing by the kernel, where every application have a separate address space and it's not supposed to see each other or touch each other data, right? So in that picture, what is a collection of objects the application must access? So to go from a network frame to the data that the web server will provide. So you obviously need CPU and hardware. We all need that with some memory. And the operating system will need to have a process scheduler and some kernel virtual memory management to drive those components. You also have a network interface card. On top of that, you will have your network driver, which drives the network interface card. You will have a network stack and a network API, which bridge the gap between the kernel and user privilege. Same for storage. You have the hardware associated to storage. You need to have a driver, which control and drives this hardware. You need a file system. All the modern operating system has a notion of file systems these days. And you need this API, which also crosses this boundary between user and kernel privilege. So in that picture, what is our perimeter? What is the API to enforce access control between each component, right? And an important rule in practice that we always have to remember is every enforcement function running at the same privilege level of its enforcement point can be disabled by the component it controls. Basically, it means inside a security domain, if one component is compromised, all the security domain is compromised, right? And in that architecture, in this picture, if you have a malware or a problem inside the operating system, and that can be anywhere inside the operating system, and this operating system can be Linux or FreeBSD, so it can be in the USB stack, it can be in the Bluetooth stack or in the PCI driver. So this particular malware will be able to tamper with your file system API, which will also be able to disable your network traffic and have access to your data, right? So the question to ask is this real? Is how complex is that stack, right? And how can we measure the complexity of what we dealing with? So I took a very known pattern, which is the defect density of code, which measures the number of line of code, obviously physical line of code, not blank line of comment. And I use CLOC, which is an open source component, which does the job very well. And there's been a lot of study about what are the defect density being the number of bugs per 1,000 line of code. And the industry average is about 1 to 25. You can get way better with a very strong development process, but still. But I will look at that open source because this is where the innovation comes, and this is mostly what we run these days. So we all run, and in the cloud, we all run a Linux kernel with those open source server. So there's been a lot of study, in particular by Coverity, which is a static analyzer, which ran a study around defect density on open source component. And depending on the line of code that you have for the user space program, those are, the defect density is about 0.69. The Linux kernel has a special treatment because it's very critical. Like I said, it's a more privileged component. And they run those analyses very regularly, and they compute an accurate defect density for the Linux kernel, which is around 0.39. So if you look at the web server, because we are in the real case of a web server, so I took the Apache web server, and you can see from the early 90s, late 90s, when Apache started, the number of line of code was around 100,000. And then it grows significantly over the year. And now with around 700,000, if you take the defect density of 0.69, that gives us 488 potential bugs. So the more interesting component will be the Linux kernel itself. So what I did is I took the Linux kernel Git repository, which is used for releasing all the version of Linux, and I built a kernel going back on time to the tag inside this repository. I went back and built a kernel for x86 and ARM, and look how many lines of code there were in at that time. So and the Git repository was going back until 2005. I had nothing before that, but since you can still see that the number of lines of code grew from 3 million to 17 million. And that's for a kernel component, even with the defect density as 39, it gives us a potential of 6,800 potential kernel bugs. And I put the reference in the slide at the end. I encourage you to go and check those coverage report, and you will see how serious those exploits are and how they get treated. So what about a component on top of that? So I look at system loader. It's a program which is responsible to bring your application in memory. So this component is responsible to guarantee integrity of what you're going to run. And this particular one, U-boot, is mostly used on the ARM platform. So very well used on pretty much all the other platform. And it doesn't get the same treatment with coverity, but I took the same defect density because it's a smaller amount of line of code, but also it's a very critical software. I assume that people will pay more attention to those kind of software, but we still have 558 potential bugs. So, and we can also look about firmware. So there's more and more open source reference implementation of firmware. And I took the ARM Trusted Firmware, which is, and I looked that implementation for the Cortex-A. And this is responsible to manage the interface between the operating system and the secure world. So it deals with all the power state coordination and all the critical aspect of the hardware. And it stays alive during the life cycle of your application. So the kernel will sometimes use those API provided by the ARM Trusted Firmware. And you can also see that the number of lines of code grew significantly over the years. And with the same defect complexity, it still gives us around 100 potential firmware bugs, right? So, and if you look at other firmware like the UEFI reference implementation or the SCPI, which is used on x86 mostly, but more and more used on ARM, you will see that we have the same level of complexity. A lot of codes and with that defect density, a lot of potential bugs. And those bugs at that level, privilege level, are obviously very important. So why are all the low-level software stack growing so fast, right? So why are they moving at that speed? And if you look at the evolution of the hardware, for example, in the Cortex-A, you will see that from the 8.0 architecture to 8.6, which is the current one, all these little bubble represent the feature that the hardware has introduced. So you have more and more hardware feature, and the developer has to provide function for that. So that grows the code base, obviously. And you can also look at the ARM reference manual, for example, which gives you the specification of that architecture. And from 4 years ago, when I look at ARM, the manual was about 3,000 pages, and today it's around 7,000 pages. So that's a complexity a kernel engineer has to grasp in order to implement properly those functionality, right? So we have all those potential bugs, but as we all know, there's real thread around that. And I wanted to look at the evolution of those threads over times. And so a lot of you probably know this history, but it first started in, well, it's not first started, but the most famous one was in 1988 with the Morris Forum, which really raised the awareness of the danger of having those kind of threats over the internet. And then 1996, we had this publication about the attack surface. How can you get those in practice? And that was very popular. So people understood how easy it was using a stack-based overflow technique to take advantage of a system, right? 1987 was also an interesting pivot point because and you can see this whack-a-mole game that's happening in that spaces. So when the stack overflow happened, there was a mitigation about how you manage the stack, the memory allocated to the stack. And a year after that, people come up with new techniques, which was return to libc. So you didn't need to execute from the stack anymore. You can just jump to existing code. And that was a precursor of all the return-oriented programming for those attacks, which was also a very important in the space of the way the thread evolved. So 2003 was also an interesting type of attack, which was an attack using a side channel over the network to tamper with an OpenSSL implementation. The interesting point there was this particular attack was able to break confidentiality in the software without any bugs. And that's still a very hard case to model, but it was really using side channel associated to the hardware. In 2007 and 2014, there was a lot of paper about microarchitecture attack, and they've been around for some time. So we're talking about them recently, but they've been around for some time. They were mostly targeting small cryptographic cards using power consumption or heat consumption from those to look at side channel. In the side channel, every time you have a difference of behavior or phenomenon that you observe, you can infer the behavior of the software, and that's become your side channel. 2014, and all those microarchitecture attack was really targeting confidentiality. They were stealing crypto keys, and they were really breaking confidentiality. 2004 was another pivot point where a side channel attack, the hardware attack mostly, was able to break integrity of software without any bug. So Rowhammer was able to change the content of the memory and change the behavior of a program. So that also was very an interesting point. And 2018, we had the well-known spec meltdown, which was basically based on the linkage from the microarchitecture associated with the side channel. And this is where the side channel become more important, because the linkage itself, it's a problem, but it's become very relevant because you have the side channel, which can show that you can steal information. Using those techniques, 2018, we had Foreshadow, which broke the software card extension from Intel, SGX from Intel, showing that this particular feature of the processor, which was supposed to give you confidentiality and integrity, but confidentiality was broken using those kind of techniques. And after, again, the whack-a-mole game, after putting some remediation from Intel, people came up with Zombieland, which was another type of attack using kind of the same technique, but showing that we can also break SGX confidentiality. So what's interesting to note over the years is all those attacks is going down closer to the hardware, which, like I said earlier, the complexity of hardware moving up provide a bigger attack surface. And since the lower you are, the more privileged you are, it's more interesting for an attacker to get control over there than focusing on the other application in user space. So hardware exploitation, just a little word on that. Like I said earlier, it's a combination of microcode linkage and side channel. They have to go together. Like Spectra is a speculation execution leak in cache, and there's a side channel on cache, mostly time channel, but timing side channel attack. So what we have to realize is those vulnerability in hardware are hardware issues. So they have to be fixed by hardware. And if you level up the hardware microcode, it's software, right? It's just using lower primitive at the hardware, but it's software, and you get update. It's like a regular software lifecycle system. And any mitigation in the operating system will include performance loss. If you try to avoid having those problems in the operating system, you will slow down the system, which kind of defeat the purpose of the optimization of the first place, right? So like Linux kernel introduced the KPTI, the kernel page table isolation for dealing with spec and meltdown. And that induced like 5% to 30% sometimes, depending on your workload. So it's a huge amount of performance penalties that you have to pay in order to mitigate those hardware problem. And we had discussion with customer in our case where they didn't want to pay that price, because when you put a mitigation like that, you also need to make sure that you have a way to disable it when the hardware will be fixed. You cannot put a new design or a new architecture in place, which will stay forever and pays its price when the hardware involved, right? So that's the issue with those attacks. So what's the alternative, right? And what the goal we want to achieve through an alternative? We want to make sure that we can constrain the TCP perimeter, so have control over the API that's needed at each layer. Also strong control over the security domain, how you can provide minimum access at each layer, privileged access at each layer. You obviously cannot change the world and propose a completely new language or new software. You need to support legacy application, and there's a lot of good innovation happening in open source. So, and obviously what you really want is to zero defect density, so no more bugs. So the TCB parameters, so how can we attack that problem? And for that, I would like to introduce microkernel. So microkernel was very popular in the 80s, and everybody was trying to run on top of a microkernel, and Mark was one of the most popular ones. There was Choresys in France also, which was very popular. But it broke down in the 80s, mostly because of performance. Is what Jürgen Linke in his first presentation at SOSP called the IPC dilemma. So everything was really slow, because obviously for the microkernel you have more component in user space and you have to pay the price for the IPC, and most of the IPC at that time was around 100 microseconds. So that was, maybe it seems okay at the time, but it was really the bigger problem of why the microkernel was slow. And Jürgen Linke proposed in the following paper that he presented at SOSP in 93 and 95, a blueprint of how microkernel should be built. And that was the beginning of the family of L4 microkernel, which nowadays is very well known. And if you look, and the problem around those IPC was really to minimize the cache footprint, and the TLB misses was really focusing on where is the real bottleneck and how you can build a microkernel which can be optimized at that level. So if you look at Nova Micro Hypervisor, which is one of the latest L4 microkernel, a message passing latency round trip in a new Intel architecture is in nanosecond now. So you have around 500 nanoseconds. So it's a factor of 1,000. So and most of the L4 microkernel will measure the latency in cycle. So you have to look at the time as well, depending on the frequency of your CPU, but it's really, really low now. So this is not a problem anymore. Furthermore, the footprint of those microkernel, because of the new blueprint proposed by Jürgen Linke, is very small. So you really have to implement the bare minimum inside the kernel, and I'll come back to that. So after the IPC dilemma, I think this day we can talk about the IPC advantage. And what the advantage that you have, and I just cited 3, which I think are very important. You get modularity, so you have better design, so you can well define your APIs, which target this TCB parameters I was talking about. But you also get composability, right? So you can build your user requirement, a specific user requirement, by taking component, the one that you need. But more importantly, I think with the IPC, you have a way to observe the behavior of the overall system. Suddenly you can see how components interact to each other, right? So you can do monitoring, logging, you can diagnose your system. It's giving you more visibility. So, and like I said earlier, the performance not being an issue, it's very important to take advantage of all those property. But obviously, like Jürgen Linke stated in his paper, this has to be built using strong design principles, right? And one of them is the principle of minimality, which state that a concept is tolerated inside the microkernel only if moving it outside of the kernel will prevent the implementation of the system required functionality, which means you put the bare minimum in the kernel. If something can run outside, then there's no reason to put it inside. And that's definitely something you can apply to all the components of a system. If you write a driver for driving with storage, you're not going to put the USB implementation inside the same piece, because this driver for USB will work perfectly outside. So you can constrain your module and your implementation at the bare minimum, right? The other design principle that I would like to expose is the principle of least privilege. And that's really around access control. So what you want is every program and every privileged user of the system should operate using the least amount of privilege necessary to complete the job. And that's really to damage any issue you will have associated to a bug, right? So you don't have to give an application root privilege because you have to have access to a specific resources. Maybe what you can do is to reduce the privilege of that resources and unify those two at the same privilege level. So what about security domain, right? Which is all about how can we get fine-grained access control, right? And for that, I want to introduce object capability. So object capability, there's two sides of that. There's a kernel side. So for the kernel point of view, a capability is an unforgeable pair made from an object identifier and a set of rights associated to that object, right? So, and that object can reference a kernel object or a hardware. But in a kernel, it's a strong composition of that object and the rights associated to that object, which is very important. From the user point of view, the capability is just a selector. So the user will just have a number, and that number defines the object and the right associated to that object, right? And the user can only do operation associated to what's given from that selector, and only the kernel knows, right? So for example, you can, if you have a semaphore inside your microkernel, the semaphore can be exposed as a capability. And if a user process asks for a semaphore, the kernel can decide, or one of the components in the system which is responsible of distributing those capability can decide you're going to get the semaphore, but you're not going to be able to down on it. You can only do up. And that's the only operation that will be enforced by the kernel every time this object will be referenced. At the Unix level, you can think of capability, an example of capability like file descriptor. So file descriptor will be a good example of capability, which reference a file and the access that you have on that file. And when you're using that integer in Unix, you don't know which file, or you created it or you inherited it, so you kind of know what it is, but you only have the operation that is given to you by the owner of that capability, right? So in microkernel, L4 microkernel, all the memory resources are exposed to capability. Even your scheduling context are exposed to capability. So you have a capability for time, how you're going to get scheduled as a user space application, which has strong control given to you by the system, right? So you can think of the protection domain or the security domain as a set of capability that a subsystem has access to, right? Operation around the capability. So capability can be granted, which means the owner of the capability will give that capability to another process, and then he will lose that capability. So it's owned by somebody else. The capability can be mapped, so that way two user process can access that resources, and can be mapped with different rights. So you can have, like I said, an access to a file which is read-write, and another capability which is access read-only, right? And capability can be revoked. In that case, you lose all the access to the specific object. So it's really a way to provide fine-grained access control. And usually inside the system, you have one component which is responsible to distribute those capability and those rights. And this is really where the principle of least privilege is important. So this component will make sure that all the operations that you have to do will operate with the least privilege that you need by dispatching the right, distributing the right the proper way, right? In those microkernel also, which things you have to note is the protection domain or the security domain is a kernel object itself. So by itself, it also has its own capability, which means if you delegate or grant or map this capability to another user process, this user process will be able to access the whole set of the object that was part of this domain. So what about support for legacy application and open source innovation, right? How such a platform can achieve that? And this is where I think we have to put hardware virtualization part of this bigger TCB, where you will have a specific application called a VMM for each VM that you're going to run, and you will be enforced the perimeter of what those VM can do just by using capability, right? But with hardware virtualization, there's a way to do more than just enforcing access to resources of the microkernel itself, right? And this is where I want to introduce a virtual machine introspection. So virtual machine is a technique which look at the state of your guess from the outside, right? And it's something that has been known since 2004. And Farai built the first product, the malware detection using virtual machine, using those techniques as well, right? So it leverages three properties of virtualization. First of all, it's isolation. So you are outside, you are completely isolated. The guest operating system doesn't even know that you're there. It gives you a way to introspect. So you have the entire state of the get state at all times. So you can really see and interact with the state if, as you wish. And it also gives you interposition, which means you can intercept and change the behavior in this interaction between software and the virtual hardware, right? But outside of the VM, you don't know anything about what's inside. What you see is just hardware notion, right? So, and this is where the complexity around VMI is really to bridge that semantic gap. So you have to be able to make sense of what's running inside that guest. So basically, you will look at the state of the guest, and the only thing you see is those sequence of bits, right? And what you really want to see is that. So you have to bring that gap and bring the knowledge of the operating system to the VMI component. So what about no more bugs, right? So Nova is the Nova micro hypervisor. It's around 9,000 lines of code. So even if I take the defect density from Linux, there's still a few bugs that exist, right? And those are same as in Linux. You don't need 6,000 or 7,000 bugs. You only need one, right? So you really want to avoid all of these. The good thing is with the microkernel architecture, you have a very modular and a very approach with small components. So the small footprint allow for formal verification of each service that you run, and that's what I want to introduce. So formal method are techniques used to model system as mathematical entities. And basically, it enables you to prove the correctness of a software according to the specification, the same way you would prove any mathematical theorem, right? So you prove that the system will behave only as specified, and which basically means that there's no bug anymore. There may be bad feature, but there's no bugs anymore. It's really what's specified that's take precedence, and it's more important. The important things about formal method, why is it possible today, was not possible 10 years ago, is the advance in proof assistance. So now you can have compute which help to verify those proofs. So you can revalidate a proof at computer speed, which is very important because the size of those theorems are way bigger to the size of the proof of any mathematical theorem, right? So you need to have a good compute assist in order to do that properly. So, and what does formal method do? It proves refinement using a simulation relation, which is a relation between state transition of system, and it relates the specification to the implementation, right? So the refinement formally captures the property that one system has a subset of the behavior of another. So basically, if you look at that graph in the implementation, for all transition that the implementation can take, there exists a transition for the specification which satisfies this relation, this simulation relation, right? So it refines the, and then we say that the implementation refines the specification. So if I take an example and we can look at the compiler, so the compiler with the implementation will generate all those states. So the compiler has the source code, you can use that as a specification, and all this code has different states. You can use that as a sequence of a state that the program will go through, and the compiler has to implement that. And it will have to satisfy the simulation relation with all the steps between the two. And this is compiled with O2, so O0, sorry, so it's lower optimization. So you have a bunch of code, but if you put O2 there, you would probably have just one line at the implementation, and you will still have a way to relate those state between the specification and the implementation. What the refinement also gives you is this notion of bare metal property. So if you have a real system connected through an Ethernet switch, right, you can prove what we call the consolidation guarantee, so the bare metal property. So if you implement that system on top of a formally verified hypervisor stack, you can prove by refinement that everything that happened in the implementation, the virtual world that you just virtualized, could have happened in the specification. So there was no new bug introduced by this, which is very important, which means a customer which has existing hardware running on different pieces of software will be able to consolidate that to a bigger equipment using virtualization, and proving those that property will enforce the fact that it will run exactly the same way. So how does it work in practice? So you need to have an abstract model of your application, and then the engineer will write the C++ source code. So we use C++ at Bedrock, and they also write this specification. The source code and the specification are processed through tools to be used by the proof assistant. And the proof assistant will also take the abstract model and using proof automation, and proof automation are really key in that space because formal method was always known to be slow to achieve. And now with the fact that we can do automation, it's really putting also the proof, the verification of the proof at the compute speed. And all those tools coming together show that your program refined to the abstract model. So any behavior that's possible for the C++ program under restricted semantic of C++, because C++ have very some obvious semantic somewhere, but you can restrict it to a certain subset, and that's behavior will be allowed by the abstract model. The interesting thing at the end of that process, the only thing that's important is the QED and the abstract model, right? And all the security property can be proved around the abstract model. Since you have this refinement property, you know that those properties will also hold to the source code. So, but let's see on the real case application, what does this look like? So if I take the web server application, what does that look like? You can now have on this platform, you can have your web server running in a separate VM if you want to implement it with virtualization, and you have your database implemented with a separate VM. So you have a clear and clean separation between the two, and you can distribute capability to make sure that the perimeters and the security domain is only the things that you want, right? So if the database doesn't have to have access to the network, the operating system, the Linux operating system inside that will not see the network interface kernel will not see the network. You can even think of a capability distribution, which gives the web server a capability with read access to the storage and goes to the database for write access. Of course, you will need some synchronization between the two, but it's really up to the user to define his perimeters and also to define his access control. You can furthermore implement that as a separate component, a very tiny component, and that will give you either more fine-grained access control. So you can make sure that, for example, your web cache may not need to talk to the runtime plugin. So only the web server can probably invoke Python or whatever plugin that it needs, right? And that also gives you modularity, like I said earlier. So every component in that picture will expose a very well-defined interface because you applying the principle of minimality, and you will be able to replace implementation very easily, right? So if you want to run a different network protocol, you can just replace the network services, nothing else, and everything by respecting the same interface and distributing the same capability, you will be able to run the same application with a different network protocol. So in our picture, what is our own TCB? What do we have to rely on for this to be strong and solid? And so what should we trust? So we should trust that the hardware operates according to the spec. And we should also trust that the compiler operates according to the spec. And we trust that the proof assistant is correct as well. That's something we have to check. So to conclude, I just expose an alternative to ensure an unbreakable TCB. And that's a composition of microkernel, virtualization plus VMI, and formal method. So in order for that to be real and practical, all the components of that bigger TCB need to be formally verified. The service, the application, the driver, the microkernel. And for that, you need to have tools which allow formal verification at scale. And I put a reference, and I encourage you to go, and there's a presentation that was done last week by Gregory Maleka, which is the person responsible, the head of the formal method at Bedrock. And he had a talk about how can we do that at Bedrock. And this is what Bedrock is about. So after that, I can take questions.
Thanks, Osman. Appreciate your coming and talking with us. If there are questions, please put them in the Q&A, and we'll make sure we get them out in front of Osman and his team as they're here ready to answer your questions. So if you have some questions, put them out there.
And like I said in the slide, I have some reference. So if I can share the slide with you, Jerry, I would be happy to give those references to people.
Absolutely. Guys, you're very quiet this
maybe I was too fast.
Maybe I can start with the one question, maybe.
Please.
If there are no other questions. No, I mean, so yeah, using formal method, of course, is a way to improve to prove the security of the TCB. But so you mentioned like these side channel attacks. So in your opinion, is it possible to use formal methods to reason about side channel attacks? Because
that's a very good question. It's a very hard problem, right? And
yeah,
I will say you may be able to. It's a very interesting challenge, but you have also to reason about the hardware. And I know that's work at MIT by Professor Adam Chipala, which tried to move formal verification at the hardware level, right? You have a project like Kami, which gives you a way to build formally verified hardware. And I know RISC-V is doing a lot of investment of that. So at some point, it's probably not to reason about the side channel attack with the way the hardware is designed today, but maybe to design a hardware with the same level of efficiency, give you mechanism to avoid those side channel attacks. Does that answer your question?
Yeah. I think this is definitely a open problem for the future,
because it's all physical, like I said, right? You have two wired. As soon as you see a difference of behavior, you can infer something what's happening behind that, right? So you have to model all this world in order to reason about the side channel.
Yeah, you probably need to model a concept of time that you don't do when you model
absolutely
instructions normally.
Absolutely.
Yeah. So other questions? Other questions? I can ask other questions.
Please.
No, I mean the other question I always have for when people talk about kernel. Of course, a lot of bugs, if not the majority, we could say that typically is maybe not the majority, but a good amount of bugs is still memory corruption.
You always have to have a memory overwrite. Yes, that's true.
There is some sort of memory corruption.
Yes.
So, and this is actually a good part of my research is on this. But some people say, okay, maybe we should just give up on fixing memory corruption and we should just write kernels with memory safe languages. And but this is not happening. And I think people are saying this since 20 years ago, or 40 years ago, but it's not really happening.
Like I said earlier, right? So there's the academic approach, the academia, which is very important. So, and it's very good that we have people thinking in those directions. But in the industry, as soon as you're going to tell them that you're going to run a kernel and it's going to run 5 times slower, even 2 times slower than this other one, unfortunately, the industry will always go to. I'm hoping with this new security challenge in the IoT world, right? So it's Internet of Things. There's no people behind, so it's not Internet of People anymore. So the things have to take decision. Maybe it will force a move further to the security world. But like I said, for the mitigation on Spectra, we had a way to re-architecture of microkernel to reduce the mitigation. With the microkernel, the space that you're exposing is very tiny, low, but still you still have user space data in the kernel that the speculation execution plus the side channel will be able to expose. But just to change the architecture of that kernel was to give us like 20% of performance hit, and customer didn't even want to hear about that, right? So that's probably the challenge of saying we're going to use a separate language. And there's also the thing I was trying to bring as well. There's a lot of background in the industry about knowledge about those existing languages. You cannot just match and replace, right? It's going to take some time to get to that.
So do you see maybe in 20 years we will have a memory safe kernel, or you think it will never happen?
If we can take the performance requirement for the kernel and also for the user space, then yes, right? But I think the approach that we have in Bedrock is to try to bridge this gap where you're still providing the innovation and you're still running the legacy software, and you give a chance to architect or implement some of the function of the kernel outside of the kernel and doing formal verification. So it's possible to run Linux inside VM, but then the networking will be outside, right? So all the TCP IP will be outside, and then you move out reduce the complexity of that kernel. And it's kind of the approach that people which was working on unikernel try to do, right? They try to reduce using principle of minimality. They say, I have this application, I only want to run this application, everything else I want to get rid of and get this vertical stack, which only implement my application. So.
Yeah, and you mentioned IoT, and unfortunately, I think IoT code is, the quality is typically much worse than, for instance, Linux kernel. So, yeah.
But
ideally the quality should be high, since these things are in everyone's house and they access a lot of important information.
Every time you put a device on the network, you have an identity. So you have an IP address, you can be rich, and the level of danger that can present, you can have an attack at scale, right? So it's not like I will attack one machine, I will attack thousands of machines or millions of machines at once, right? And it's not like in a IT world when you can restore your environment in a few minutes and you will probably lose some money, but it's just money. In the IoT world, you will lose life, right? So if your self-driving car has a bug and need to be patched, right? The cycle to repatch that software and to take the proper action, that's not, it doesn't scale. So you need to have a better stack. And that's the reason why, like I said, when I started to talk about Bedrock, the idea was really that is, how can we provide a clear, strong foundation to build software on top without losing all the innovation, but at least we have a strong foundation. Today, the problem is everything is built on sand, right? So if you break underneath, like you break the hardware, you break the kernel, everything's collapsed, right? And that's cannot be a solution for the new world of IoT.
Yeah. Any other question?
I don't see any other questions, Professor.
Okay.
Well, Osman, we really appreciate you taking time to speak with us today.
My pleasure.
You know, it's been a long time coming. We've had to change a lot of things around it to make everything happen. So we really appreciate the team from Bedrock joining us today, and hopefully this won't be the last time we'll have a chance to talk.
Thanks a lot, Jerry. Thank you.
Sure.
Thanks a lot
for your
inviting.
presentation.
Thank you.
Bye.
Bye-bye.
Bye.